Modern AI image editors can produce remarkably realistic images. In this example, the model is tasked with turning on a light bulb. The result appears plausible at first glance, but is the predicted lighting actually correct? To investigate this question, we introduced the 3D-LP benchmark, consisting of 1,000 real-world indoor image pairs captured with a light probe switched on and off. For each scene, we captured 2 9-exposure brackets. The exposures are averaged to reduce sensor noise and merged into a single HDR image. The same process is then repeated with the light bulb turned off. Next, we annotate regions that are particularly informative for lighting evaluation, including metallic, reflective, and transparent surfaces. We also label ambient highlights and shadows, as well as highlights and shadows cast directly by the light source. Additional annotations identify the light bulb itself and all visible windows. For each scene, the dataset contains both a real light-off image and a real light-on image. One image is provided as input to the model, which must generate the corresponding alternative lighting condition. In this example, the task is to turn the light on. Evaluating these predictions presents a challenge. The exact color and intensity of the generated light may be ambiguous, even when the overall lighting effect is correct. To account for this, our metrics are designed to be invariant to both factors. The generated image and the corresponding real image are each divided by the real light-off image, producing 2 ratio images. After standardization, the ratios are compared using a mean absolute error. We refer to this metric as the standardized intensity error, or SIE. Capturing overall light falloff requires a different approach. For this purpose, we introduce a second metric, the low frequency error, or LFE. The behavior of these metrics becomes clearer in a zoomed-in view. In the red region, the model predicts too much illumination around the light bulb compared to the real image. This discrepancy appears as a large error in the SIE metric. The blue region reveals a different failure mode. Here, the shadow cast by the power bank is predicted at the wrong angle, resulting in insufficient illumination on the floor. While SIE measures local intensity differences, LFE focuses on the broader distribution of light. In this example, SIE reports a substantial error, yet LFE indicates that the overall falloff pattern is captured reasonably well. Using these metrics, we evaluate 6 state-of-the-art image editing models on both light-on and light-off editing tasks. Among the tested models, Nano Banana Pro achieves the strongest overall performance. Nevertheless, all models continue to struggle with complex scene geometry and challenging materials such as glass and mirrors. This example illustrates a common failure mode. Although the generated image appears highly realistic, the predicted highlights on the black shelf are incorrect, and several shadows are not reproduced accurately. These results suggest that photorealistic appearance alone is not a reliable indicator of physically correct lighting. Significant challenges remain before image editing models can consistently reason about illumination in complex real-world scenes. For additional details, please refer to the paper and project webpage.